Welcome back, and this is the second in the series of videos looking at Kinetics II. So in this video we're going to be looking at reaction profiles and what they can tell us about the mechanism of the reaction and the rate equation. So you're going to need your notes, and we're starting on page 7. So what we have here on page 7 is the reaction profile diagram for the SN1 mechanism we looked at the end of the last video. So here we have our halogenoalkane and our nucleophile, and here we have our intermediate carbocation. Notice that it's basically two reactions. So there's a reaction to form the intermediate carbocation, and then there's a reaction to form the products. Need to be careful of the difference between a transition state and the intermediate. Transition states are found at the peaks of these curves, whereas intermediate carbocations are actually like products and reactants formed at the minimum. So they are real molecules which really form, whereas the transition state is a little bit more fluctuating. It's not really a real molecule, it's the stage that it goes through, or at least we can't catch it doing this step. So in the previous video we looked at an SN1 mechanism. We're now going to look at an SN2 mechanism and how its rate equation differs. So we're going to take simple halogenoalkane such as bromomethane. Still has my dipole on it, delta negative, delta positive, and it still has my nucleophile, my OH negative. But this time two things happen simultaneously. The lone pair from the OH groups attacks the delta positive carbon, pushing the electrons out from the bond onto the bromine. And this one has this funny species that we put in a box. We put in a box because it's very difficult to catch it. And we say that at this point, bonds are being formed between the oxygen and the carbon and being broken between the carbon and the bromine. The negative charge is being transferred, but we're not too sure where it is at the moment, so we're going to put it on the outside. And because this OH group can only attack from the opposite sides of the leaving group, it's important that the bond angle between the two dotted bonds is 180. And then we finally get our product, our methanol, out the other side once that electrons have been completely transferred, and we get our Br negative ion. So the rate equation for this reaction, this only actually happens in one step. This is an elemental reaction. So the rate is the rate constant K times the concentration of the OH negative, and there's one of these in this step, so it's raised to the power 1, and one of my halogenoalkane, also raised to the power 1. So this is an SN2 mechanism. Why? Because it has two species in the rate determining step. So if we look at what that means on a reaction profile, you'll notice that it's only one step, and it goes via this transition state. The transition state is up the top of the peak. It can't be isolated or observed. It is simply an arrangement of atoms that we're going to postulate from thermodynamics. There's no intermediate, so there's no double dip, if you like, and our reactants and our products are at the minimum of the curve. So looking at the reaction profile on the next page, we have our reactants and our products going via a transition stage. So the activation energy for the forward reaction is quite low. The activation energy for the reverse reaction is very high. So we can say that the products are kinetically stable with respect to the reactants. In other words, it's very unlikely that the products would have enough energy to go backwards. What's happening in this part of the curve, the upward part of the curve, is we are breaking the bonds because this is an endothermic reaction, this part. We get to this transition state. Here, very unstable. The species have the maximum amount of enthalpy. Enthalpy is going up the side. And then as they go more towards their stable state, they are making bonds, this is releasing energy, which is why you're coming down here, you're giving energy out to the surroundings to come to your final products. So these are concepts we've come across before, kinetic and thermodynamic stability. So reactions are kinetically stable when the activation energy is so high that the reaction happens too slowly to be observed at room temperature and pressure. Thermodynamic stability is where the products are thermodynamically stable with respect to the reactants. In other words, they're lower down on an enthalpy level diagram or a reaction profile. So the rate of our reaction is going to depend on both the entropy change and the activation energy. So in this last section of this video, we're going to be looking at these Maxwell-Boltzmann curves. We've looked at these before in Kinetics 1, but just to remind ourselves before we move on and look at catalysis. So we have two curves where the temperature at T2 is higher than the temperature of T1. So the average kinetic energy, in other words, if I was to measure the temperature, it would read a value here for T1 and here for T2. In other words, I've raised the temperature. But it is only those particles with an energy greater than or equal to the activation energy, this is my activation energy point, that actually have sufficient energy to react. And you can see there here, by increasing the temperature, I've increased the area under the curve, so therefore I've increased the number of particles that can react. Things you need to remember about this one, you always start this at the origin because no particles can have zero energy, unless you can get to absolute zero, which we can't, so it's kind of a limiting factor. But even the coldest of particles is going to have some kinetic energy. It might be very small, but it'll still be there. But at the other end, we don't intersect the x-axis even at higher temperatures because there is a vanishingly small probability of finding a particle with a very, very high kinetic energy. It is a very small probability, but it is not zero, so it can't intersect with the x-axis. So if you remember, we looked at our area under the curve as we went from T1 to T2. So the area under the curve to the right of the activation energy line is increasing. And this is the main reason why, as you raise the temperature, you get a faster rate of reaction, because there are an increased number of molecules whose kinetic energy is greater than or equal to the activation energy. And that's the key factor. Two things to consider when you're increasing the temperature. The fact that the molecules have more kinetic energy means they move faster and more likely to collide. But that is not the overriding factor. The overriding factor is the fact that more of those molecules will have an energy greater than or equal to the activation energy. So you'll get a higher proportion of successful collisions and you'll get a greater total number of successful collisions. I'm going to change that slightly to per unit time. In other words, you get more successful collisions in a particular unit of time.